I hope you all enjoyed the kind of holidays theme with gingerbreads and gloggy and ugly sweaters and everything. So hi, I'm excited to give the first talk. And my talk is about memory and how JavaScript manages memory. And it is going to be a little bit intense, so I hope you're not tired. So first of all, hi, my name is Kateryna. I'm originally from Ukraine, but I live in Estonia for the last 3 years. I work at Veriff on developer productivity, and I also lead our front-end guild. And yeah, I'm just really excited to give this presentation to you all. And I think it's our biggest meetup yet, so it's really cool to have so many people here. And I hope you like it. So I will talk about memory management. And how it all started is that we all know that eventually everything in the computer becomes a bunch of zeros and ones. And one time, it was in the middle of the night. I remember like 3 a.m. or something. I got really fascinated on how specifically does that happen. And there's a lot of materials online, but they cover often like one part of the problem, how garbage collection works or how that works. And I wanted to kind of create the full picture and fill all of the gaps. And with all of the things that happen there in between. So with that, I went down the rabbit hole trying to understand how it all works and plays together. And today, I want to invite you to the same rabbit hole. And I just want to show you around. And hopefully, in this kind of really visualized, you'll see a lot of things happening here. Maybe you can turn on the light a little bit off so that people can see the slides better, because there will be quite a lot of stuff happening there. And I think that would be useful. Can we do something? Yeah? Yeah, just so that the slides are a little bit more visible. OK. Oh, yes, that's nice. Can you see it better right now? Yes? Yes, good. Good. We found the button. Cool. So with that, let's start. And let's start with those zeros and ones, and a little small introduction into binary. So 0 or 1 is how computers generally represent information. It is kind of a smallest fraction of information there is. It's like on and off switch. In all these computers, there were literal light bulbs, right, with like light on and off. And in the modern computers, in the hardware level, it determines basically whether there is current or no current. And it's called 1 bit of information. And within this binary, we can represent almost any information there is. Small numbers, a little bit bigger numbers, characters, emoji, and even the answer to the ultimate question of life, universe, and everything. OK, I like that you got the reference, yes. But how do computers actually store and represent that information inside? And there's different types of memory and storage computers use that store those zeros and ones in unique ways. In some cases, there's like film that reflects light differently. In some cases, solid-state drive. But if we are talking about the memory our JavaScript applications use, it is usually RAM, or random access memory. It's basically like working memory that CPU uses when running all of the application processes on the computer. And let's see a little bit how it works. So first of all, we need a memory cell, which is basically kind of this little box, let's say, that can store 0 or 1, or can store charge for some time. On the hardware level, it is implemented as an electric circuit of transistors or a combination of transistor and capacitor, with an idea that it can basically store charge for some time, and you can read to it, and you can write to it, and you can read from it. But with one cell, we cannot really do much, right? So in order to kind of work with more cells at once, we can organize them in this kind of grid. And to access one specific cell within that grid, we need to address it somehow. And RAM uses something similar to like street and house address in real life. So here is the address there. You can see it right there. And we can take the first part of that address. It basically specifies the column that we are looking for. And the second part specifies the row that we are looking for. And then we can retrieve what is being stored in that cell. And yeah, we just read 1 bit of information. That is really cool, right? But it's not really a lot, right? We probably need a way to operate with more bits of information at once. So for that, we can arrange these matrices that we just talked about in a grid. And with the same address, we can address multiple cells at once. So basically, with the same address, we are kind of getting the cells from multiple grids, and then we are able to read a bigger chunk of bits together. So in this case, we read this. And in order to simplify, we can move up a level of abstraction and just see it as the address and data that can be stored within that address. If I convert it to decimal right now, it will be 88. And then we can put all of those addresses as this kind of like continuous array of available addresses and data that can be stored within them. So in this case, we used 8-bit addresses. It means that in total, we can store only, we can store only 256 bytes of data. And it is really not a lot, right? It's probably less than your average like image or something that you store on your computer. So modern computers operate on not 8-bit, but rather 32 or 64-bit architecture. It means that the addresses got really, really long. And usually, we right now use this hexadecimal format to represent those addresses. So in real life, they look something like this. This is basically the physical representation of RAM, where we have addresses and data that have been stored within that address. And it is physical memory. And when our applications run on the computer, they do not use physical memory directly. Operation system maintains what is called a virtual memory. It basically dedicates a chunk of virtual memory per process that then that process can utilize for itself. And then it maintains a mapping of where chunks or like pages within that virtual memory correspond to the actual addresses on the physical memory. Why it is needed? Because yes, in some cases, yes, we can fit everything in the RAM, but in some cases, RAM can run out, right? And in those, then we can just move some of the things to the hard drive without ruining the abstraction for the process itself. So for the application, basically this virtual RAM is everything they have, and they use it, but then under the hood, operating system manages it effectively. And also there's like multiple, those like virtual memories dedicated per every process. So it means that within the physical memory, some chunks will be dedicated to your process and to other ones as well. And the virtual memory also has the address that does not equal address in the physical memory itself. So for example, this address here can be a completely different address on the physical RAM. Are you following me so far? Yes? Yes? OK, cool. Thank you. I needed that feedback. So if we look at this kind of virtual memory array, it is also basically the same structure. It also has addresses, and it also stores bits of memory within them. And when we are running our application, often, if we have a variable, let's say if it's an object or a string, it might not fit into 8 bits. 8 bits or 1 byte is like really small. Only certain most of the things actually don't fit into it. So let's say we have variable foo here. We usually would need a bigger segment of memory to dedicate to that variable. And usually there's something that is called a pointer, right? So basically then this foo points to that specific location where the segment of memory where it is stored starts. And in languages like C and C++, you can actually work with pointers directly. There is a class that you can work with pointer. You can free and allocate manually your memory yourself as a developer. But in JavaScript, we rarely need to think about memory at all, which is actually a good thing, right? Because JavaScript is a pretty high-level language. It means that a lot of problems are solved for us already, and we can just focus on providing business value, developing features, without thinking of like memory organization, pointers, and so on. And it is all done automatically for us by JavaScript engine. And engine itself is just a program, just a piece of software that takes your JavaScript code, which is essentially just a piece of text, parses it, and transforms it into machine code that can be understood by CPU. And there are different engines out there. These are some of the most popular ones. We know V8, SpiderMonkey used in Firefox, developed by Mozilla, and JavaScript Core, which is part of Apple's WebKit and used in Safari, and among others. And in this talk, I'll focus mainly on V8, which is probably the most popular of all of them. It is used in Chrome and other Chromium-based browsers, Node.js and Deno, Electron, among others. It is also open source and written itself in C++, so you can actually go and check out the source code yourself as well. It's kind of hard to navigate, but you can find some things there, and there's a lot of documentation that goes with it as well. So now, let's take this very small piece of code and go through how it can be stored within the memory that V8 manages. So following my Alice in Wonderland's analogy, let's follow this white rabbit into the rabbit hole. So there are two types of memory that V8 uses. There is stack memory and heap memory. And it's not something that is unique to V8. These are common computing terms that are used in a lot of other programming languages as well. And stack is the region of memory that allocates local context. When interpreter goes through your code by line by line, it stores the local context when executing your code. And heap is much bigger region of memory that stores everything that is allocated dynamically, say your objects, functions, arrays, and so on. And in our case, we have an object rabbit that is will be defined in a stack, but first we need to store it somewhere in the memory. So within the heap, we'll have the object itself, right, with the color variable, and the color itself will be actually stored in a different location. And within the object of rabbit, there will be a pointer to that specific location where a string white is stored. And kind of going back a little bit, these are actual segments in the virtual memory that correspond to the kind of segments in the virtual memory. And these are, here there's like the pointers, they're like really short, just for the kind of presentational purposes. In reality, they are way longer. And as our program runs, more and more things get allocated on the heap. And if we zoom out a little bit, we can see that within the virtual memory that is dedicated to our application, stack and heap are located on the opposite sides. And they kind of grow towards each other into the free space. And of course, our program needs to share the general memory with other programs and other applications that are running on the computer. And also with other tabs and browser plugins in the browser, which kind of gives a little bit more insight why Chrome can be so memory hungry sometimes. Yeah, I love that GIF as well. And now let's explore a little bit more complex examples. How are you following me so far? All good? Yeah. The GIF is really nice. But if you want me to slow down, you can just do this like as Ross and Friends, and I'll try to go slower. So let's get back to our example. We already know how the object itself represented in the memory. Let's say we define another variable, and it stores the same string weight. How then the string will be allocated within the memory? Of course, we can just dedicate another segment within the memory and store the same string, but it probably wouldn't be very efficient. Therefore, V8 uses something that is called string interlining, and basically duplicates that string, and both of these variables will be storing the same pointer pointing to the same location in memory. And all of the primitive values in JavaScript are immutable. Therefore, we can afford something like that, right? So every time it's changed, the new memory will be allocated and is deduplicated by V8. Now, let's say we want to change foo's value to a different string. So in that case, we will have that string, we'll kind of allocate memory for that string here, and then pointer that for the foo variable will change to the new location. And often, when we think about variables, we think of them as kind of like boxes that store values within themselves. And that's how often we are taught to think. But I actually really like Dan Abramov's analogy in his Just JavaScript course, where he kind of compares variables more like wires connecting. And I think that makes a lot more sense to kind of use that mental model. So in this case, color variable is just a wire connecting to the place where white string is stored. And when we are creating foo initially, it just connects to the same place. And when we are changing, the wire just moves to a different location. Let's explore another example and look at how objects work within the memory itself and dive a little bit deeper into the objects. So we have an object here right now. There's two properties. And then we assign this variable to another one. And then we change the new one's name to a different value. If we try to log out the original rabbit's name, it will be changed as well. And this is something that is called modification by reference, right? When we updated the value here, it updated here as well. Before kind of exploring more, let's look at how it actually happens in the heap. So we define the rabbit object. This is something that is already really familiar, right? But then when we create another variable and assign rabbit object to it, both of these will basically be pointers to the same location. So there will be two wires connecting to the same place. And then when we are making a change, because it is the same place, it will be updated in both of them simultaneously. And because these variables are basically pointers to the same place. And most of the variables in JavaScript are actually that. They're pointers to different locations on the heap that, where something is stored. And if we look again with our mental model, we can see that this is something that happens. So when we change here, it is basically changed in 2 places at once. So we see right now, name is updated in both of the objects. This is something that we can avoid, right? We can, for example, add spread operator here and spread the rabbit object. And then when we are updating the name, it will actually stay as the original one. So when we're using spread operator, this is what happens. It basically defines the new objects and copies all of the pointers that are on the top level there. But you see that they will be still located, kind of pointing to the kind of all strings there. And then when we're changing, we will see that both of them right now have different values. Interestingly, it works for all of the nested objects as well. So for example, if we had a nested object here, and the same way we use the spread operator, and we update the deep nested property within the code of color here, it will update it in the original as well. Why that happens? When we are using spread operator, it's basically creates the new object, but then the code within the another rabbit object is basically pointing to the same location here. And then when we are updating the color, you see that it is updated in both of them together. And this is something that can be tricky sometimes and can create, if you're not aware of how modification by reference work and you're not careful about how you're modifying your objects, it can create some bugs that are really hard to find. Because, for example, if you're using React and you receive an object in props and you're doing some modifications within the component, it can update in parent component and in your Redux store because all of them are basically pointers in the same location. And we talked a lot about memory allocation right now, but what about memory freeing, right? We allocate all of the stuff there, but at some point, some of the variables and objects that we have just allocated the memory for, they are not needed anymore. So for example, as this one here, you see this white string, it's not used anywhere anymore. So this is something that can be considered garbage. And again, in languages like C and C++, you actually need to free memory manually. But JavaScript engine does it for us by running a garbage collector. And right now, we'll dive deeper into how garbage collection works. But before that, let's understand how, from V8's perspective, it can understand whether something is garbage or it's not. So when we are running our application, we can represent all objects we have as this kind of chain of references that goes from the root and kind of follows all of the references there. As our program runs, similarly to that white string there, some of those references just stop existing. And then, if they are not reachable from the root anymore, they are not needed. So we can, if we look at the memory array, we can basically free that memory. And use it for the new allocations. But the problem is that often it leaves our memory fragmented. You see there's like a lot of little gaps there, and it kind of becomes harder for us to allocate something new because there is not a lot of free space available. So in order to fix that, we also often need to compact the memory back so that we have a bigger chunk of free memory available for the new allocations. It is similar if you use like really old Windows machine. I remember being like frightened by this utility, but there was this disk defragmenter utility where it basically did that for you in the old but current operating systems, they actually do it automatically, but often like V8 also needs to do it for you as well. So let's look a little bit how garbage collection works within V8. So if we look at the heap, we need to look at 2 sides of it. There is basically the whole heap is split between 2 what are called generations. And we will understand why they are called generations a little bit later. But there is basically a young generation and an old generation. And this is where all of our objects are stored, right? Let's look at the young generation first. This is where all of the new objects get allocated. So basically, as you create the variable, it gets allocated here. But within the young generation, it is split into 2 equal parts. And right now, we'll see exactly why. They're called like from space and to space. And the names will make sense in a bit. So as our program runs, we kind of allocate and allocate new objects and new objects into the heap. But then at some point, there comes a time where we are trying to allocate something, but then there's just not enough space in order to fit it in. So this is something that triggers garbage collection cycle. So here, garbage collection comes in. Oh, can you see it? Yes, there's the garbage collection here. So let me just like a little bit so you can see the garbage collector. And it works, it is often called stop the world garbage collection because basically it stops the whole execution cycle and collects all of the garbage you just created in order to free space for the new stuff. So the way it does, it goes through the whole chain of references we saw before. Remember the diagram? It basically traverses through it once and understands which objects are referred to within your code, right? And then after we understand that which objects are alive, we can copy them from space to space. And that's why they're called like that, right? So we copy from one space to another. And right now, after we did that copying, we can delete everything else. But before deleting, we need not to forget to update the references, right? So it goes and updates all of the references to those objects that we had before. Then everything else can be removed, and these are swapped in place. And then garbage collection here finishes. It finishes. It finished. And now we can continue the execution and allocate space within the memory for that variable that was waiting. This algorithm called the scavenger, and it is really fast, but the problem that it is really memory hungry. You see that we always need twice the amount of space that we need to get garbage collected. So it is okay for small amounts of space, but probably wouldn't work for the whole heap. And that's why we have the old generation. So V8 follows what is called generational hypothesis. And it sounds depressing, but it says that most objects die young. So basically, most of the stuff that you create in your code gets allocated and almost immediately gets unreachable and can be deleted. And if you look at how you write your code, it actually makes sense, right? So if you have your function and you create your temporary variable, return something, that variable is not needed anymore anywhere, right? So almost immediately becomes unreachable. So that's why they're split in young and old generation. And as young generation fills up, and we run the garbage collection cycle, the objects that survive the first cycle are marked. So we mark the objects that have already survived the cycle once as these kind of intermediate. They're called like intermediate generation sometimes as well. And then, after it fills up again, and we run the garbage collection, among those who survive the second cycle, all of the intermediate ones get promoted into the old generation instead. So now we are thinking, okay, they probably will stick out for longer, and we can put them into the old generation. And old generation, let's talk a little bit about how garbage collection works here. How are you? Are you? Yes, so far? If I need to go slower, you can do this, right? Old generation actually takes up most of the heap. This is where most of the stuff gets stored. And is way bigger than the young generation. For the garbage collection, it uses what is called mark, sweep, and compact algorithm. So basically what it does, it traverses through the whole chain of references and marks, that's why mark, right? It marks all of the objects that are reachable. Then it can sweep, identify the non-reachable one, and they can be removed. And then it also needs to compact the memory. And compaction, and basically because the old generation is so big, the way that the memory is allocated there and the way it is compacted is actually really interesting. So let's look into that. So the whole heap is divided into equal segments. They're called pages. So here we can see, for example, there's more pages than 4, but for our example we use 4. And each of those pages is basically a segment of memory where something gets, where we can allocate stuff. And the problem is that since there's so much space, V8 needs to understand where it can allocate something new and where it cannot. So as our program runs and we free some memory, there are usually some kind of gaps become available within those pages. And V8 maintains what is called free lists, which is basically like Airbnb for memory. So they're basically all of the free locations get stored here. So if you look at our example here, so we have 3 locations of size 1 available. So we store them under size 1. It is all categorized by size. And then we have also 3 locations of size 2 available. So we can store them there. Of course, there's more sizes than that. This is just like very hypothetical. And the way it works is that when we need to allocate, so for example, the new object gets promoted into the old generation, V8 will look in the free list to understand where we can put it. So it goes through the free list and finds the first available spot, and then we can allocate that object there. And then we can, of course, remove it from the free list because it's not available anymore. But at some point, still, even with that, some of the pages become just way too fragmented in order to work with them. And V8 has this internal heuristic that understands which pages need to be compacted. So which pages became too fragmented for the new allocations. In that case, what it does, it basically does something similar to what we kind of saw before. Basically evacuates all of the filled spaces within the page into the new page. And then we have a bigger continuous chunk of memory available that gets put into the free list here, and then it becomes available for the new allocations as our program runs. So, how are you holding up? All good? Yes? Okay. So, I've been already talking for almost 30 minutes, and we covered quite a lot of different aspects. So, we looked at our how code in JavaScript gets run in the runtime environment, then processed by JavaScript engine, which uses stack and heap inside. That gets garbage collected. Can you see, right? Then it uses the virtual memory array. That uses the physical RAM inside your computer, which stores zeros and ones. And we kind of went through this whole cycle. But the interesting part about it is it's only actually kind of part of the picture. There's way more things that happen under the hood. For example, like V8 creates hidden classes, and the way of generally it maintains all of the heap objects and so on. There's a lot of cool things that kind of there's still a lot to learn. And this is something that I generally love about programming. There's like, no matter how much you know, there's always a lot more to learn. And I hope you liked this overview and you learned something new, maybe understood a little bit more things about memory management. And with that, yes, I want to say thank you. And yes, I hope you liked it. And you can find me on this social media. And I'm from Veriff. I didn't say that. I work with Veriff. And yes, if you have some questions, let's do that. But if I could get like a glass of water or something. Because I didn't have any, and I was just like, so that would be really nice. Oh, thank you, I really needed that. Thank you. So, do we have any questions? I think there are also some gifts for questions, right? So the best question, and I get to choose. I get to choose which question is the best.
Yes.
Okay, I choose which question is the best, and then the person will receive a gift. So, and use the t-shirt, the one that Misha is wearing. Can you show the t-shirt? Yes, that's
This is our model for the day?
Yeah, this is the model for the day. Yes, so, yes, I see your hand.
Yes, sir.
What, Mike, okay, yeah.
This one is not for the gift, because it's a stupid one, okay? Just to clarify, you started with this reference to C in C++ with pointers. Pointers in C, they refer to physical or virtual memory?
Basically, all of the processes in the computer use virtual memory.
Okay, in
yes.
So is there any way to have access to memory in JavaScript?
Physical?
As in C, in principle.
Oh, basically, as a point, basically to access the pointers. As when you're writing your code, basically no. So you cannot see, like, for example, what is the pointer for this specific variable, but you can see heap snapshots. So for example, you can, in some, there's, when you're running Node.js, there are some parameters that you can put out, and where basically then you can see basically pointers and all of that within V8, and you can see it in the heap snapshots as well.
So if even you really wanted and you want to hack, no way.
Yeah, basically it's, yeah, there's, at least from my knowledge, maybe I don't know something, of course I don't know anything, everything, but no, I don't see that happening. But you can actually, if you use like snapshots, there's like memory tab within DevTools. You can actually find, for example, the basically where your variable is stored, how much space it occupies, the internal structure of heap object, and so on. And I didn't cover it within this talk because it would be kind of too much, but it's kind of really fascinating to kind of like look there and see how they're all stored, and especially since, I'm sorry, is it going too much? Or but since JavaScript is not typed language, right? V doesn't know how much space your object will occupy. So the way that it manages, like when it grows, I kind of found that also really interesting. And you can see it in the heap snapshot, which is kind of cool. Okay, there's another hand there.
Is there a way to either trigger garbage collector or stop it, just in case you want to shoot your leg?
I think, so again, like, I haven't done it myself, but in Node.js, in Node you can configure some of the parts of how garbage collection happens. In browser, like, I didn't find any, but maybe there some exist.
Very much unlikely.
Yeah, also, yeah, kind of.
It's sandboxed.
Because basically if you have, in Node you can configure some of this stuff, but yeah. Did I answer the question?
Thank you.
Yeah, so we've covered V8, and mostly, I guess we've been speaking about Node and, well, okay, Chromium. But are you aware of any prominent differences between the engines in terms of memory management? Are all of them known to be using reference counting for garbage collection, or do some of them experiment in the space?
I mean, there's of course some like differences between how different engines like implement things. In my research, I mostly dug into V8, so I don't know like the specifics. But yeah, I haven't really researched much about how like JavaScript core or others work that much.
Okay.
But, yeah, sorry.
Don't fight yourself, don't fight.
Thanks. First of all, these are probably the best slides I've ever seen.
Oh, I can show you how it's done. Yeah.
So you did some extensive research on V8, and do you think there is point to care, as a developer, to care about memory?
That's a good question. I think in most of the cases, it's kind of like good to know some things, for example, about modification by reference, which we sometimes ask it on the interviews and find that quite like significant portion of people don't know about it, but this is something where you can actually shoot yourself in the leg sometimes. So this is where I think it's really important to be aware how things are kind of like stored and so on. On the level that I covered, I mean, not really. I don't think like most people actually like need to know this, but it's kind of cool, right? it's cool to know things. But also sometimes if you have some memory leaks, understanding a little bit the internal structure and how things work can help you to be more productive and looking for those and solving those memory leaks. Understanding the heap snapshots and how those work, I think, yeah, could be interesting. But also you can just like brag about it and like on the interviews or something, which is, I don't know, very worth it. Yeah.
So I wanted to ask, so since JavaScript has no types, actually, is there any way the engine can predict what the types of objects it actually deals with?
Yeah. It is. Yeah, it's a good thing. So basically, V8 maintains what is called a hidden class. So as your code runs, so this maybe just example. Well, yeah, let's take this like Rabbit object, right? So basically, as you create the object, it creates internal structure within the heap object itself that says color white, right? And then if you change it, if for example you add name Jack, then it will update that hidden class. And basically, as you update the object, it will maintain the hidden class as well. But it's not very smart. And that's also an interesting part where you can optimize things when you know about it. Because V8 also has this, let me just, I have actually some skipped slides here that I didn't cover. And I just want to show you the V8 things. Let's unskip this. Unskip it. Give me a moment. I'll just unskip and I'll show you the diagram basically. So this is the one. So basically within V8, this is how like general structure how V8 works. And there's two kind of compilers, right? There's like one that is like stupid one, like interpreter, that's called ignition. But then there's an optimizing compiler, because if you would just go line by line, it probably won't work really fast. So the optimizing compiler tries to find different patterns in your code to optimize it to run kind of faster. And it actually uses those hidden classes that I talked before. So for example, objects have the same structure, and you're running them through the function. You can even see how it gets optimized. You basically cast through a lot of code of how it can work, but it also has the optimization part, so that if you, for example, pass object to that function that has different structure, it will just kind of fall back into the just like stupid interpretation in a way. So that is kind of like really interesting bit I also found. I didn't cover it here, but basically just maintains the hidden classes. I can share some resources on the topic as well. I have a bunch of different links and kind of like cool stuff. Yeah.
Thank you.
In the context of those hidden classes, how do you think is using TypeScript, which will produce more like better structure of types? Because lots of people who use pure JavaScript, they have like garbage in types. They add some fields to one type and so on. So will using TypeScript improve performance? Because the types used in Memory will be more like predefined and structured. How do you think?
It's a good question. I think you're a pretender for the t-shirt. I don't know specifically, but I would imagine that they would do something like that. The problem is that when those hidden classes, when it works with them, order matters. So color white name Bob and name Bob color white are basically different classes. So and I'm not sure how kind of TypeScript handles that. But I imagine that TypeScript developers probably thought about
if you use TypeScript, you will just make some order in your types instead of like adding fields to one variable.
Basically,
you will have like two different objects.
Basically, it just strips the type notations. It doesn't modify the code a lot. With the modern target, it will
maybe
change
you can get
the
the mic, because I think that will be not
sorry. So I can comment on this. So most TypeScript is trying to maintain the structure of your code the way it is by just stripping the type notations. One exception is enums that both live in types and values, but that's mostly the only exception. So if you, essentially what's mentioned here, like you have color and names in your object as two properties, if you change the order in your code, it will still be valid TypeScript. I guess, I'm pretty sure it will not reorder them, and you will not get this optimization for free. So you need to do it yourself. Basically, if you are producing objects with classes, then it's the same as JavaScript, and you get the fixed order of fields. If you're producing objects as literals, the order of fields will not be optimized by TypeScript.
No, thank you. That's yeah.
I don't think you understood my question.
No, I think
people who write in JavaScript, for example, we have like two structures. One with like fields from 1 to 10, and they will just add to that structure different values, and in some point will like strip from their 5 fields to another type. But if you use TypeScript, you will make order in your types instead of two, like one garbage type and another normal type.
I'm just
you will just make like 3 nicely predefined classes.
Yes, so sorry to interrupt. I'm just thinking that it's kind of like pretty goes in like pretty deep discussion. Maybe we can discuss it during the break,
Okay.
and then I have some other questions.
Okay. Yeah.
Sorry.
Oh, thanks. Also, you have to look into how WebAssembly works. Basically, the original WebAssembly is doing exactly this. They compile to, they know the heuristics, how the JavaScript estimates the memory usage, and then they do completely weird things if you look at the output, which is to trigger this heuristic. on purpose to make the pre-allocation optimal. So if you compile C to WebAssembly, that's basically how it works. My question was, how does the decision get made if the whole memory for the process grows, or if garbage collection kicks in, or when can it shrink again? How does it interfere with the per process memory?
To be honest, I haven't really dug deep into that specific topic, but I would imagine that it works as for any other kind of like process that you run in your computer. So it would just kind of grow when it needs to grow and then managed by the operating system. But maybe you have some insight on that.
There is the max size when you
yeah,
run Node.js,
there's a maximum size, and Node.js you can customize it as well with some of the properties. In the browser specifically, I think it is basically managed by browser engine in a way. That like if you have multiple, that's my assumption. I haven't really kind of read specifically about that, but my assumption that it will be managed by kind of like a browser engine that will kind of look at how tabs work and then kind of change a little bit the memory usage. But I don't know. This is like a good thing. Maybe there's something on Stack Overflow to read about. Actually, after the questions on Stack Overflow, and V8 maintainers answered me, so it was kind of you can maybe ask that there as well.
Yeah, I'm going to come back to the previous question. So TypeScript cannot be always trusted. The thing is like you have let's say, okay, so you have keys 1 to 10 for the object, and the second type has 1 to 5. So you think TypeScript would, let's say you create one with less properties, and you use the spread operator, you will still get all of them. Like you can define the type, but TypeScript really doesn't care.
Yeah, thank you. For the no, do you have a question? No? There's one hand. How much time do we have? Do we have how many questions?
Let's have 3 more questions.
3 more? Okay. Yeah, there was a hand. Okay, yeah, go.
I wanted to ask, a great talk by the way. Why did you bother going so deep? Like, was there something wrong when you were developing?
No, there was nothing wrong with my code necessarily. I didn't need to, but I just wanted to. That's how my brain works. And sometimes if I like have like something that okay, and I have like y, and then I go into that, and I get another y, and then it just kind of goes into the rabbit hole. When I just found myself at 6 a.m. when I need to have a meeting at 9, looking at some kind of CS RAM memory architecture courses on YouTube. So it just happened, and then I thought this would be really cool to share some of the things as well.
Yeah, it was really cool. And my next question is, did the way you write your code change in any way at all after knowing all this stuff?
No. I mean, I knew quite some things. So I knew kind of like in general how like garbage collection works and references and so on. I think those are the important things. But about the specifics, it's just kind of like, sometimes it's like really cool to know some things, and just learn them for the sake of learning them. And I think that was for me, and I hope you also found it kind of cool to know. And I didn't really, right now I don't really write that much code, so maybe it will when I start writing more code, but not yet.
Hey.
Hey. Hi.
I have a question about the memory management. So, when you call some function in JavaScript, engine creates for you the kind of lexical environment. This is kind of object which contains the arguments, argument values, something from the closure, something pointer to outside context, etc., etc. So the engine kept it inside the system object. So my question is how the garbage collector manage these objects and where these objects stored?
I mean, it's basically the same as any other object, right? So like So I looked in inside the heap. There is this class called the heap object, which is like a superclass for everything that is allocated on the heap, like strings, objects, arrays, and so on. I didn't look into functions specifically, but I would imagine, compared to how it works for objects and arrays, that it is just like a series of pointers within the structure. So it's nothing different to that. Basically, it still counts all the references, and under the hood it is still represented under just like a series of references, things referencing each other, and once some of them stop existing, I imagine it gets garbage collected in the same way, but we also have maybe somebody else knows, maybe there's something different, but from my side, I think it's kind of just works in the same way.
Got it, thanks. One more question, maybe I missed something. Does Node.js or our engines have some settings that I can manage the type of garbage collector? For example, in Java, in JVM, we can define the garbage collector, arguments, command line arguments. Do we have something similar in JavaScript?
You can customize some things in Node as properties, and then there's just like, I don't know specifics, so I looked at them, but I already forgot. But basically, there are some customizations that you can do. Choosing garbage collector, I don't think so, but yeah, but I don't think you can. It just kind of comes with V8, but I can be wrong. So.
Cool, thanks.
Okay, that's all, right?
One last question.
No, wait, there was 3. It was already 4.
So, we shouldn't close the cycle. The first person to ask the question will ask the last question.
Thank you so much. I hope you will not allow me to ask a question.
It's okay afterwards.
Thank you so much. So, TypeScript was mentioned also. It's a big presentation. So my question is it any potential place for competitor, alternative for JavaScript in the future, or maybe now?
Oh, this is such a loaded question. I'm more like JavaScript, like I don't know. Competitor, but I mean, there's already some kind of like competition going on, but. Yeah, I think basically with the JavaScript, the thing it is like the language of the web in a way, and also needs if you want to have something, and it also depends, of course, like if you write on the server, you can just use any other language, right? But if you look at the web, basically this is what the browsers support. So most of the stuff gets like if you use some other language, it eventually gets kind of transformed into JavaScript. But yeah, I don't know. You probably should ask a different person. Yeah, that is all. Yes.
Yes.
And I would be happy here. Like we have break, right? We have pizza. Yes.
It should be. There's like a courier running around Tallinn somewhere, and it's like basically converging on this place, but no pressure, right?
Okay. So we'll have pizza. And then there's some snacks, and I would like to catch a breath, and then maybe if you have something to discuss, we can talk. And yes, I hope you liked it.
But before we need to think of a question.
Oh, I need to pick a question. Yes. Okay, I already forgot most of the questions. Oh my god, I really did forget. So, I remember, let's choose you. Yes.
Yay!
Yes, you will get a t-shirt. And you can also pick the gift under the tree as well. If you didn't get one yet. So, but yes, with that, we have a break.
So yeah, guys, we have a small break.